We
Okay,
right,
we're recording. So I'm very happy to welcome you all back to MOPA for the spring semester, and we are starting off with Arseniy Sheydvasser. I apologize if I mispronounce that. Who's speaking on higher rank arithmetic groups uniformly bi-interpretable with arithmetic. Go ahead, Senya.
all right. Thank you very much for coming. Thank you to the organizers for really allowing for me to invite myself somewhat unceremoniously, but it's a pleasure to be here. So I want to talk a little bit about joint work that I've been doing with Finitely at Technion. We'll get there eventually, but let me begin with a bit of motivation. I should maybe preface with a disclaimer. I'm not a model theorist. I will say this outright. I'm a number theorist who's sort of stumbled into this. So any apologies if you see something and you think, well, this is trivial, because it wasn't trivial to me. All right, but in any case, so let's begin with the following problem. So let's write LGU to be the first order language of groups. All right, you have the standard notion of elementary equivalence that, if I have two groups, H and H prime, then they're elementarily equivalent if for any first order sentence in the language of groups. The sentence is true of one of group if and only if it is true the other one.
Sanya,
Yes.
I apologize. I will be rudely interrupting that, and then, but quite often it's not often clear what is the standard language of groups, because you do have a choice. Is everything included? Or is the inverse included?
Oh, that's a good question. I don't know that it makes a difference here, but let's say yes.
Because for some results it does. Usually it doesn't, but for some subtle results.
Right. I don't think that for anything that I'm saying here it matters, but let's say that the inverse is included. Sure. Very good. Right. In any case, so an obvious way that it can happen that things are elementarily equivalent is if the groups are just isomorphic. But if they're infinite groups and the converse does not hold, you can prove this. If you're a model theorist, you can prove this in terms of Wash's theorem, in terms of using the compactness theorem, just sort of constructing non-standard models, that sort of thing. But even if you're just a group theorist and you care about things that are finitely generated, you can get examples. So for example, there's a result of this Salah that all free groups in at least two generators are elementarily equivalent. So we might ask this.
Sanya, and also
yes.
Another rude remark: at CUNY there are usually more names associated with this result.
Oh, okay. No, that's fine. Which ones?
Tikov and Karwampovich.
Okay. So this goes back to my assumption that I'm not a model theorist. So I apologize wholeheartedly if I miss any citations, examples. This is entirely due to ignorance and not malice. But very well. But yes, so the question that we want to ask is, like, what restrictions can we put on a group such that if they are elementarily equivalent, then we can actually say that they are isomorphic. So the one thing to consider is this: if say we restrict ourselves to considering finitely generated groups, we might consider the following property. We say that a group is first order rigid if another finitely generated group is elementarily equivalent to it, then it follows that they're in fact isomorphic as groups. Of course, finitely generated groups in general are not first order rigid. Free groups are not. More generally, torsion-free hyperbolic groups are not. But there are positive results. So for example, there's a result due to Avni, Lubatsky, and Miri from 2019, which says that irreducible, non-uniform, higher rank arithmetic groups of simply connected, absolutely simple algebraic groups are, in fact, first order rigid. Now, of course, I realize that I'm not speaking to an audience of number theorists, so perhaps a little bit of background would be appreciated at this juncture. So let's do a crash course in algebraic group theory, basically. So to start, I will write K for an algebraic number field. So this is just a finite dimensional extension of Q. Think Q joined to square root of 2, Q joined to cube root of 2, these kinds of things. I will write O of K for its ring of integers. You should think of this as sort of the maximal extension of the integers inside of your algebraic number field in some sense. There's various ways that you can define this formally for its maximal subring that is finitely generated as an abelian group. It is the set of solutions to integer polynomials with leading coefficient 1. But it conforms to kind of what you expect. It is just the integers in the case of the rational numbers. It's something like z adjoint square root 2 in the case of q adjoint square root 2, and so on. It's sort of a discrete subring in some sense, with the right notion of discrete. We'll also need the notion of places of our algebraic number field. Again, there's various ways to define exactly what this means. Sort of the most standard probably is to think of them as equivalence classes of absolute values defined on K. So norms, norm maps into R, which are also multiplicative. We say the two absolute values are equivalent if they induce the same topology. But the way that I personally prefer to think about it most of the time is that the place is basically split into two pieces. You have the ones that come from prime ideals of your ring of integers. And then you also have the definite places, which come from embeddings of your field into the complex numbers. And of course, the complex numbers have the usual norm, which is just square of the real part plus square of the imaginary part, because square rooted, right? And so if you have an embedding of your field into C, then it inherits that absolute value. And sort of a third way that you can think about this is in terms of completions of your algebraic number field. So the idea is that if I have a place of my algebraic number field, well, thinking of it as a absolute value, it defines a norm, which defines a metric, which defines the topology. So now I can think about Cauchy sequences, and I can take the usual completion in the way that you learn in real analysis, and you get this completion, which I will denote by K sub nu. And this will be one of two things. If my place came from a prime ideal, it'll just be an algebraic extension of the p-adic numbers, or it'll be one of either the real numbers or the complex numbers. If this came from one of the definite places, one of these embeddings into the complex numbers, right? And the reason why I need to talk about places is because unfortunately we're going to need the notion of S integers. So the ring of integers is important, but we need something a little bit more flexible. So here's what we do. We take our collection of places, we take some finite subset which contains all of the definite places. You can think of this as you have the definite places, and now I'm throwing on some finite number of prime ideals, if you prefer thinking about it this way. And then the ring of S integers, you can define it in any of the following completely equivalent ways. So it's going to be a ring which is, you know, a bit larger than the usual ring of integers. You can define it as the set of elements in your field, such that the norm of such an element is less than or equal to 1 for all of the places not in your marked set. You can define it as the set of places which are in all of the extensions of your ring of integers in each of the completions, coming from places that are, again, are not in your marked set. But personally, I find that the easiest way to think about it is this third way, but you think of it as follows. You say, all right, what is an S integer? It's a quotient of two elements in the ring of integers, A and B, such that I have restrictions on what the denominator is. It should only be contained in a prime ideal of my ring of integers if that prime ideal is in one of these is one of these marked places. It's an S. So I'm sure some examples would be welcome here. So the most boring example, of course, that I can give you, as always, is just the integers inside of the rationals. The set of places here is just the one infinite place. But we could, for example, add on one more place. This will be coming from a prime ideal, and the corresponding ring of S integers will be Z joined 1 over P. So that'll be integers where we're allowed to divide them by powers of this prime B. Or, you know, generally speaking, what this look like in Q is I can add on some finite set of places. This will be some finite set of prime numbers, P1 through Pk, and then I'll be looking at the set of rational numbers where the denominators are only divisible by these prime numbers, P1 through Pk. And one last example, not in Q, but in an algebraic extension, take Q joined to the square root of -14, and the base ring of integers will be Z joined square root -14. But if I want something you know, a little bit larger, maybe I throw on a prime ideal over the prime 3. So there is such a prime ideal which is generated by two elements, by 3 and by 1 plus square root -14. And so then again, I will be looking at these quotients where the denominator has to be divisible by powers of 3 and powers of 1 plus square root -1 square root -1 over 14, but not sort of anything else, basically. All right. Any questions so far? Okay. In that case, let's talk about algebraic groups for a bit. There's a modern notion of algebraic group scheme, you know, in terms of algebraic geometry. You define schemes, you define these as topological spaces. I'll be quite honest, I don't know this theory so well. I prefer thinking of this in terms of very classical terms. In our case, we're always going to be thinking about linear algebraic groups anyway. So the way to think about this is as follows. Take some ring of S integers and consider a collection of polynomials with coefficients in this ring of S integers. This is basically what we're going to think of as being the scheme. In terms, why do we say this is an algebraic group scheme? Because we have to have a restriction that the set of solutions over this group of over this ring of S integers should be a subgroup of the general linear group over the base field K, GLN K for some n at least one. So we get it as a subgroup we get it as a subgroup of invertible matrices. So the way that you should think about this is that I have some set of polynomial equations. I consider these solutions to these, and this is a group. These things, because they're matrices, their multiplication is defined in terms of polynomial relations. So basically everything is polynomially defined products, inverses, all of these things. They're nice maps. So if I consider, for example, the set of solutions to these polynomial equations over K, so this will be some algebraic group. It's an algebraic variety, if you like thinking about these things, where group multiplication, group inverses, these are all morphisms. So in general, we're going to write wherever this makes sense. If G underscore is an algebraic group scheme, we will write G underscore R for the set of R solution where R is wherever this makes sense. Again, let me give a few examples here. So I can take this special linear group. And these are going to be n by n matrices with a determinant 1. If you think about the determinant, this is a polynomial condition. So we have a polynomial equation being set equal to 1. So this is certainly fine. This obviously sits inside of GLN. So all is well. Here's another example. Let's suppose I take a quadratic form with coefficients in my ring of S integers. So for example, I might consider this quadratic form x squared minus 3y squared. This is defined over the integer z. And then I can consider linear transformations of this vector space Kn, which preserve this form, in the sense that if I have a vector, its image under this linear transformation evaluates to the same element if you apply the quadratic form to it. And the collection of such linear transformations is the orthogonal group, which we denote by O of Q, pardon. And the collection of such of these orthogonal transformations, which with determinant 1 is we denote by SOQ. And these are both algebraic group schemes over our ring of S integers. Again, this is sort of easy. It's easy to check that all of these conditions are polynomial in nature. And one final example, which I have to give, is the trouble here is with something like SOQ, unfortunately, is that so you can think of these as topological spaces. So you can ask about them being connected. And as a result, you can ask about covering spaces, essentially. And the trouble here is that SOQ has sort of non-trivial covers. So, and sometimes this matters for various results that you want to use. So you want to go upwards and find sort of the top covering spaces. This is the universal cover. And in the case of SOQ, this is a group known as spin Q. It's not entirely obvious that this is the case, but it is also an algebraic group scheme. It's sort of a finite cover. You can describe this all completely explicitly. It's a little bit messy, so I don't particularly want to do it here, but I will ask that you sort of take me at my word. The way that you should think about a spin of Q is that it's more or less consisting of orthogonal matrices, but with some minor alterations, basically. And the reason why we care about it is because it is sort of the simply connected variant of SOQ. Great. All right.
Seni, can I ask?
Yes.
Are these these groups are all sort of defined by some collection of polynomials? Are
Yes.
we insisting that this is somehow a finite collection or a definable collection or some, like, is it a recursive? I don't know, is there some
I see.
some condition on how large such a how we're defining these groups?
Right. So for, I mean, look, these are always going to, okay, so it's always going to be a finite set of polynomials. I guess I should, yeah, let me just put it that way.
Okay, that's fine. Thanks.
Yeah, no problem. I don't know, and I'm thinking whether you need to assume that it's a finite collection of polynomials or whether you can prove it by Notströlenstadt. Well, that doesn't matter. In any case, the answer is that it's always a finite set of polynomials. So all of this, like if you're thinking about defining this in the theory of arithmetic, yes, you absolutely can. And this is going to be relevant later. Yeah. Great. So there's one final thing that we need, which is we need the notion of an arithmetic group. So I know I mentioned earlier that you can think about the set of K points on this algebraic group, and this gives you some nice variety. And if you like, you can if you don't like algebraic number fields, you can replace this with, say, the complex numbers, and then you get a Lie group. So you can think of this as a manifold. And then you have S integer points, so some sort of discrete set of points. And this, in some sense, we want to think of as being arithmetic. Okay, so we definitively think of the set of solutions in the ring of S integers as being an arithmetic group, but somehow this is restrictive. We'd like something a bit more general. How can we do this? Well, we say that a subgroup of G underscore K is arithmetic if it is commensurable to this sort of prime example or example of an arithmetic, where, as a reminder, two groups are commensurable if they're sort of almost isomorphic. They contain finite index subgroups, which are isomorphic. So there can only be a little bit of difference between them in some sense. And again, I can provide examples. So, all right, so the example, of course, is SLN-Z. And so, if you're ever bump into someone in a dark alley and they say, well, give me an example of an arithmetic subgroup or your life, you tell them, oh, SLN-Z. That's, of course, as a subgroup of SLN-Q. So again, the set of places here is just the one infinite place. Here's another example, which is commensurable to this one. So consider the group the subgroup of SL2Z generated by matrices 1201 and 1021. So you can show that this is, in fact, the set of matrices in there of the form 4a plus 1, 2b, 2c, 4t plus 1. And sort of because it's defined by congruence restrictions, it follows that it is commensurable with SL2Z. So that's one way to think of it on the one side. But on the other hand, if you think about how these matrices 1201, 1021 act on, say, the hyperbolic plane, then you can show that there's actually no relations between them. They generate a free group with two generators, exactly these two. So we're getting that you can think of the free group on two generators as an arithmetic subgroup of SL2Q, which is sort of cute. One other example, let's take SONQ. So this is the special orthogonal group where I take the quadratic form to be just the most boring one, x1 squared plus x2 squared plus up to plus xn squared. So SONQ, what is this? It's really just, it's the collection of rotations of the n-1 sphere is what it is. And the point is that that's a compact group. So when you look at arithmetic subgroups of this is a discrete set. So what discrete sets are also compact? Finite ones. And so you get that the arithmetic subgroups of this group are exactly just its finite subgroups. This is somehow a little bit boring, but you have to bear in mind that examples like this happen. But already here, like we see we have some varieties. Like we see that some arithmetic groups are very obviously first order. No, we saw that for finite, we get finite subgroups. Finite subgroups are always first order rigid, very trivially. On the other hand, some arithmetic subgroups are very obviously not first order rigid because we saw we got a free group on two generators. We saw earlier that those are not first order rigid. So so clearly it cannot be all arithmetic subgroups. We need some additional restrictions, which I'll talk about in a second. Let me give one other way of constructing arithmetic subgroups because they come up later. Let's suppose I have my ring of S integers, and I take an ideal inside of it. Right. So if you like, this is right. Okay. An abelian subgroup which is closed under the under multiplying by elements in the ring. Right? Usual thing. So there's a reduction group homomorphism. Right? Like if I take any S integer, I can consider reduction modulo A, modulo this ideal, and this gives me a group homomorphism from my set of solutions in the set S integers to the set of solutions in this quotient subring. So that's interesting. Now, let H be any finite subgroup inside of this inside of this quotient. Well, a set of solutions inside of this quotient. Then its pre-image is going to be an arithmetic subgroup of my group G of K. This is a congruent subgroup, and the reason why we call it a congruent subgroup is because it is a very nice description. It's you start with your example, G of the S integers, and then you add on some congruence restrictions, some congruence relations. such and such polynomial should be 0 mod A, that sort of thing, or 0 or 1 mod A, but whatever it is. And this is all still completely definable. That's the beauty of it. All in terms of first order logic in the language of arithmetic. Great. Right. So here's a concrete example. Like, consider SL2Z. Now consider all matrices of the form AB to CD, and this will work out to be a congruent subgroup that is defined by congruence restriction system. Obvious. You just need the lower left coordinate to be 0 mod 2, but it is also closed under multiplication, so it is a sub. Okay, so let's get back to this theorem that I stated earlier, that irreducible, non-uniform, higher rank arithmetic groups of simply connected, absolutely simple groups are first order rigid. I've defined sort of many of the group, many of the words in this theorem. What we mean by arithmetic groups, what we mean by algebraic groups. I still owe you a few technical things which I don't want to get too bogged down into, but sort of very briefly, an arithmetic subgroup is reducible if it is commensurable to a product of arithmetic subgroups, and it is irreducible otherwise. So we think of these things that are indecomposable in some sense. Any arithmetic subgroup you can embed as a discrete subgroup inside of the sort of completion with respect to these marked places. And so then you can consider the quotient of this by this discrete subgroup, and you can ask whether that quotient is compact or not. And we say that a lattice is uniform if that quotient is exactly if that quotient is compact. So we have to ask in this theorem that we don't consider any uniform examples. Only non-uniform ones are allowed. Again, I mentioned very briefly that we can talk about these groups being connected with respect to the Zariski topology, and so we get a notion of simply connectedness by considering sort of the right generalization of covering space. Again, I don't want to spend too long on this because one could, and people have written textbooks about it, and I only have an hour and not 6. But one thing I do want to mention briefly is this notion of rank. Like, what do we mean by higher rank here? So for any place of my number field, I can do the following. I can consider the completion case of mu. I can consider this group of solutions in case of mu. And then I can ask about tori inside of this group. Now, tori for an algebraic group theorist means the following. It means I have some closed connected algebraic subgroup such that I can diagonalize it. There's, it might not initially consist of diagonal matrices, but I can act on it by conjugation by some element in my group until I get just a collection of diagonal matrices, and then I just ask, well, what is the length of these diagonals, and that exactly is the rank. And for us, higher rank is basically always going to mean that the rank of the scheme with respect to each of these places in S, the sum of those is always at least 2. So what this prevents us is studying any sort of trivial examples. Like, for example, we had the example of SON, right? And we saw that its arithmetic subgroups were just finite ones. This is one of the things that this prevents. This prevents us from considering cases where the rank is so low that we get bad examples, like of that sort. Okay, so I should give you some examples and non-examples. So the example of an arithmetic group satisfying this theorem that you should have in mind is PSLNZ, which is just, I take the special linear matrices and I quotient out by plus or minus the identity. As long as n is at least 3, this will be an example. Some non-examples that I should mention. So SLNZ for n bigger than or equal to 2 is not an example. Why? Because it's not simply connected, is basically what it is. PSLN Z is the universal covering space. It sits right above SLN in some sense. So that's a non-example. PSL to Z is also not an example. It is simply connected, but unfortunately its rank is just 1. So no dice there. Here's a much less trivial example of something that does not fit this mold. Choose any positive square-free integer d. Consider a quadratic form defined on Q joint square root d as follows. It looks like minus square root d x1 squared, minus square root d x2 squared, and then there's just plus x3 squared plus x4 squared up to plus xn squared. The spin group of this quadratic form has every single nice property that you would want. It's simply connected. The rank is certainly large enough, etc. But unfortunately, this is uniform. As a lattice sitting inside of sort of its completion, it is co-compact. So this is a non-example. So you cannot use this theorem to conclude that this is first-order rigid. A little bit of a spoiler, it is first-order rigid, and we will show this a little bit later. All right. Great. So, any questions so far? All right. Very good. In that case, how should we generalize Avni, Lebowski, Nimieri's results, right? Like is there some more general theory that can get us to first order rigid? Like, okay, great, we have this large class of examples that are for first order rigid. So maybe there are other examples. And so here's one such way to do this. This uses the results by Philippe from 2007. But suppose I have a finitely generated group, which I can show is bi-interpretable with arithmetic. Then it follows that G has to be first order. All right, so so I should say here that when I started this project, the notion of bi-interpretability was new to me. You all are the experts here. You're probably more familiar with this than I am. I don't know if we have any errant number theorists looking, but I think that there will be some number theorists maybe watching later. So let me give a very, very sort of brief rundown of what I mean by this. So the idea is that interpretations give us a way of constructing models of one first order language inside of a different first order language. So first of all, if I have a first order theory L, and I have a model M of it, by an imaginary of M, what I mean is it's a definable subset in the language of this theory, D of M sub n, quotiented out by, again, some definable equivalence relation. All right. So yeah, it's some sort of quotient set that's I can reasonably define in terms of my first order theory. Now, what do I mean by an interpretation? Suppose that I have two first order theories, LL prime. I have models of them, M prime. By an interpretation of M prime and M, what do I mean? It's 2 bits of data. I have an imaginary I of M and a bijection from I to M prime, such that for any relation symbol of the target language L prime, its pullback is definable in terms of the language L inside of my imaginary of M. And for any function symbol of L prime, sort of the same thing. I can pull it back to a function on I, and this should also be definable. Sort of, there's a more intuitive way, of course, of thinking of this, is that basically what's happening is that I construct an imaginary of M and definable relations and functions on it, definable in its language, which turn it into a model of the other first order theory, L prime, specifically one that happens to be isomorphic to M prime. So all of the same first order sentences are true of them. So they're elementarily equivalent, and also there's a bijection. So basically what we're doing is we're finding a copy of M prime inside of it in a definable manner. And yeah, the benefit of this is that, you know, if I have imaginaries of M prime, then I can pull them back to imaginaries of M, which are sort of isomorphic copies, but definable over on that side. All right, so a very basic example. I take SL2Z. I think of this as a model of the first order theory of groups. I think of the integers as a model of the first order theory of rings. I have this subset of Z4 of quadruples ABCD such that AD minus BC is equal to 1. This is clearly a definable set, so this is an imaginary of Z. And you know, it's not hard to see that, you know, the obvious map from I to SL2Z, this defines an interpretation of SL2Z inside of Z. And then the only thing that I think I switched the order. I think it's Z should be on the left and SL2Z should be on the right. That's okay. Right, like the only thing that you sort of need to check here is that group multiplication is definable, but again, these are sets of matrices. Multiplication of them, these are just polynomial relations, and that's clearly definable in the language of rings. So all is well. Okay, and inverses as well. If we're including this as something that we need to worry about. So great. We say that self-interpretation of a model is trivial if this bijection that we use to define it is definable. I'm running perhaps a little bit low on time, so I'll mostly skip over this. The one thing I will say is that one interesting fact, it's a theorem of Aschenbrenner, Khalif, Nazir Zeno, and Scanlon from 2020, is that actually all self-interpretations of arithmetic are trivial. Okay, this is an example of a non-trivial self-interpretation for groups. If anyone wants to see this, perhaps at the end of my talk, we can go back to this. I want to make sure that we cover the rest. Okay, so so now we can say what a bi-interpretation is. So I have two first-order theories, L prime. I have models of them, M prime. A bi-interpretation is a pair of interpretations, M prime and M and M prime, such that if I compose these two compositions, this gives me two self-interpretations of M and of M prime. We ask that both of them are trivial. So the corresponding maps are all definable. And in this case, we say that these two models are bi-interpretable. And the whole point is that I can take imaginaries on one side, move them over to imaginaries on the other side, and vice versa. And so theorems about definable sets carry over. So as an example, if something is bi-interpretable with arithmetic, then we know that, for instance, all self-interpretations have to be trivial. And again, from that same paper by Aschenbrenner, Khalif, Nazizan, and Scanlon, they prove that every finitely generated infinite integral domain is bi-interpretable with Z. In fact, they prove something a little bit stronger than that. Really, we don't even need something quite that strong. We need something a little bit less strong, which is that all of the rings of S integers are bi-interpretable with arithmetic, with everything defined in the language of rings here. Right. As an example of something that's not bi-interpretable with arithmetic, no non-abelian free group is bi-interpretable with C. And there's lots of ways that you can see this. Like, for example, you can show that non-abelian free groups have non-trivial self-interpretations. So, great. All right. So how can we use this notion of bi-interpretability? When does this occur? So here's an example. There are others. So let's suppose that I have an algebraic group scheme over some ring of S integers with the usual requirements. We want it to be simply connected, absolutely simple, higher rank, et cetera, et cetera, et cetera, and satisfying at least one of the following two conditions. Either G of K should contain unipotent elements, or alternatively, it should be a spin group of some quadratic form in at least 9 variables with coefficients in my ring of S integers, which is non-degenerate, which I might define as follows. If you diagonalize this quadratic form, there are no zeros on that diagonal. So every single variable appears, as maybe perhaps another way of phrasing it. It's not secretly a quadratic form in a fewer number of variables. No. It's very much in all of them. And the other thing that we have to ask is that there's some place in my marked set such that the rank of the group scheme at that place is at least 2. So it's not, I can't get away with just asking that the sum of the ranks has to be at least 2. I need one particular place where that happens. Sort of unfortunate. And then I ask that gamma should be a congruent subgroup of the solutions over the S integers, which does not has a trivial center, just consisting of the identity matrix. In that case, gamma is bi-interpretable with C. So this is an interesting theorem in that it is in some ways weaker than the previous result by Avni, Lebowski, and Mary, and in some ways it is stronger. So on the one hand, it is a little bit weaker because we're not just taking gamma to be an arithmetic subgroup, irreducible, I suppose. We actually have to insist that it be a congruent subgroup, sort of has to be a little bit more specialized. But on the other hand, before I mentioned that we had to insist that our arithmetic groups were not uniform. In particular, they could not come from these spin groups of the type that we have here. So those were not covered, but here we actually can get them. So that's the first way in which it's stronger. The other way that it's stronger is that bi-interpretability tells us more than just first order rigidity. So certainly it tells us that all arithmetic groups as defined in the above theorem, I will call this condition star, are first order rigid. Again, this is my results due to Khalif. But we get plenty more. So here's an example. For any arithmetic group gamma in star, there exists some one first order sentence corresponding to that group in the language of groups, such that if I take any finitely generated group delta, delta is isomorphic to gamma if and only if delta satisfies this one first order sentence. For first order rigidity, you knew only that there was some set of first order sentences, but that set could have been infinite. But here, no, there is just one. It is entirely a definable property of being isomorphic to such an arithmetic group. The other thing is, because we're getting it that it's bi-interpretable with arithmetic, we get all of these results that carry over from the fact that
so it's just a quick question about this second corollary.
Yes.
So is there any more, do you get some concrete information about what this phi gamma actually is? How long is it?
Oh,
is it an existence proof, or is it some effective procedure to get such a phi?
Right. So okay. Most of the methods in this theorem, I think they can be made effective, but as written in the theorem, they are not. So I want to say that you should be able to figure out what such a first order sentence is, but it might be excruciatingly difficult because you would need to go through this entire paper, and every single time where it says there exists a constant such that this occurs, you have to figure out what constant it is exactly. And I don't think anyone's done this. Even I have not done this. So is there anything non-effective used in there? Maybe even there is.
My question is very
Yes.
naive, because one of the things one could ask you when you say for any arithmetic group gamma, how is this gamma given to you from which you can extract this information?
Yes.
What is it that you need to know about gamma?
Right. No. I understand, Roman. It's so the trouble is what I'm worried about. What I'm worried about is that the interpretations are not given to you in a way that's completely explicit, right? I mean, right, in order to translate from one to the other, from one theory to the other, I need to be able to tell you exactly how we're defining something like addition and multiplication inside of my group, inside of this imaginary, in an explicit way. And and it isn't quite, like I'm saying that this could be made explicit, I'm pretty sure. But it's the short answer is I'm not entirely sure. I would have to think about it more. Probably consult with Fen as well. He knows these things better than I do. But let me sort of leave it at that for the time being. And I apologize if that's not a very satisfactory answer. Is that okay?
Oh, sure. No, it was a naive question. I didn't really expect a precise answer.
Okay, very well. Very well. Okay. Right. And yeah, you get other nice things like the first order theory of arithmetic groups in star is undecidable. For the I guess the way that I should phrase this is for any particular arithmetic group in star, if I consider its first order theory, that first order theory is undecidable because the first order theory of arithmetic is undecidable.
Senya, I apologize.
Yes.
So is this a new result in the sense that you get some new groups about which you didn't know whether the theories were decidable or not? Or is this confirmation of something that was known before?
No, I think that this is new. I think for some of the groups that we considered this, where this is considered, this is perhaps not new, but I want to say that at least for the spin groups, this is I want to say this is definitely young. because I don't think other results covered. Right. Right. And of course, all of the finitely generated subgroups of arithmetic groups in this set are definable. Okay. Right. Now, I want to sort of finish by talking about extensions that I have been doing with Fen to all of this. But in order to do this, we need to generalize this notion of bi-interpretability a little bit. We're going to need sort of a uniform notion of bi-interpretability. So for this, let me first give a notion of uniform definability. So let me fix a first order language L. Let me consider a sequence of models, M sub n, with sort of no restrictions on what these models have to be, but I want to talk about definable subsets of the sequence of models. You know, the most sort of obvious way to do this would just be to say, well, I want a sequence of definable subsets inside of each of the M sub n. This is too loose. There's not enough structure here. We need some sort of uniformity across the entire sequence. So here's what we do. We say that a sequence of definable sets, A sub n, of the models M sub n, is definable. It's a definable sequence of subsets if there exists some one first order formula, phi of x1 through xk, y1 through yl, and a sequence of these parameters y1 through yl for in an in an such that sorry, that shouldn't be yn and an, that should be yn and mn, such that an is exactly the set of elements in mnk which satisfy this first order formula. So this is just the usual notion of a set being definable with parameters, with the one restriction that we're asking that this definition work across all members of the sequence, the same formula. Right? So it's sort of it's a uniform definition. Right? And you can do, in a similar way, definable sequences of relations, functions, imaginaries, sets of sets. It's the same idea. You ask that these things be defined all in terms of some fixed first order formulas. Okay. And now we extend our notion of interpretation to sequences of models. So again, I have LL prime as first order languages. I have sequences of model MN and MN prime. And by an interpretation of one and the other, I mean the definable sequence of imaginaries in one and a sequence of bijections from these imaginaries to the target sequence, such that the pullbacks of all the relations, the pullbacks of all the functions are definable sequences of relations and of functions. So it's again the exact same notion of interpretation as before, with just the one trick that we're asking that whatever formulas that we use, they all have to be the same everywhere in the sequence. The notion of self-interpretation of a sequence being trivial is again the same. We ask that the sequence of bijections be definable, right? And again, this is a little bit stronger than asking that it be a sequence of definable bijections. And then with that, we can talk about a bi-interpretation with such sequences. It's exactly what you expect. It's two interpretations such that their compositions are trivial. All right. So this is a uniform notion of bi-interpretation. And when can we get this? So again, here's another result by Avni and Miri from 2020 now. So consider the set of all arithmetic groups, PSLD of some ring of S integers, where D is bigger than or equal to 3. To be clear here, we're allowing ourselves to vary both D and this underlying ring. This is still, however, a computable set, and in fact, it's recursively enumerable. So choose any such enumeration of all of these arithmetic groups, gamma sub n. This is just some sequence. And what you get is that such a sequence is going to be bi-interpretable with arithmetic, which we think of as a sequence of just z, 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 z ad infinitum, right? So what's interesting about this is that, okay, we get that each of the gamma n's is bi-interpretable with arithmetic. I mean, that's great. We already had this from our result from before, but we actually get a little bit stronger because this is done in a uniform way. We get results like the following. So this is like a uniform version of a result that we had before. It's not just that there is some first order sentence in the language of groups that defines any one of these groups, PSLD, OK joined S. Actually, there is some one sentence in the language of groups such that if a finitely generated group delta satisfies the sentence, then it has to be isomorphic to one of these groups, PSLD, ring of integers of ring of S integers, for some choice of D, some choice of S integers, which is I don't know. To me, this is sort of very surprising because it's sort of telling you that arithmeticity, in some sense, well, here it's a very limited one, but is first order definable, which you wouldn't expect. This really, you look at a group like PSLD, ring of S integers, that looks like you need the language of arithmetic in order to define it. But no, it's much more simple. Okay, and let me end with I guess sort of my own work with Chen on this. So this is an analog of the preceding two, this is sort of a synthesis of the preceding two theorems. In the case of spin groups, so I put a theorem with a question mark here because while we're quite certain that this result is true, we haven't quite finished writing up the paper, so this isn't even on the archive yet. So I want to give myself a little bit of wiggle room in case we have to add a few more, another condition at some later point. But I'm fairly confident that everything will go through. So here's the idea. Remember that we had this collection of spin groups in the earlier Avni-Miri result. Centralist congruent subgroups of spin groups of over a quadratic form Q, where Q is some, again, non-degenerate quadratic form in at least 9 variables. I need to ask that the rank at least some places at least 2, and consider enumerating all of those. The only thing that's different here, the only addition, is that I have to ask that the collection of places is no more than some constant, which I call S sub max, which we can choose freely. We fix a constant and then we consider all such arithmetic groups which satisfy this condition. Consider this the enumeration of all of them, gamma sub n. Then this sequence gamma sub n is bi-interpretable with arithmetic. And this again has the same sort of benefit that we can uniformly define such spin groups. So there, for any choice of this constant S sub max, there exists some first order sentence phi in the first order language of groups, such that a finitely generated group delta satisfies the sentence if and only if it's congruent to some spin group of this type, which is, again, I find this sort of to be very surprising. I will note that we're fairly certain that you can remove this restrictions, that the number of places cannot be too large. But we're not entirely sure at this moment how to do it. So hopefully when this is actually published, this will be removed, but perhaps not. Chen seems to be a little bit more optimistic than I am that it can be done. He's also more of an expert than I am, so in some ways I defer to his judgment. Okay. All right, so I'm a little bit over time, so let me do the following. I can talk a little bit more about what these interpretations are, how they're constructed, if people are interested, but let me leave that as something for us to do as sort of questions. For the moment, let's sort of end, at least nominally. Let me just say thank you very much for listening, and again, thank you again to the organizers.
Okay, thank you, Senya, for the wonderful talk. Let's all thank Senya. Yeah, I'm happy to open up for questions, and feel free to just unmute yourself and jump in. Okay, in that case, I will start. Is there this a lot of this hinges on this result that being bi-interpretable with arithmetic implies something about this property of rigidity. Can you say
Yes.
something more about this result? Is this sort of easy? Is it, or is there some, is there some simple
Right.
idea of this proof, or is it like somewhat involved?
So I don't think it's very difficult. Well, okay, no, I should be a little bit careful, because I think I want to say that you need to combine what Khalif did with what Avni, Lebowski, and Miri did. I actually wanted to read Khalif's paper before this talk. I had a better sense of this. Unfortunately, that paper is in French, which I do not speak. So I was, but from what I understand and remember, I think the key points is that if it's bi-interpretable with arithmetic, then the group is prime and quasi-finite axiomatizable. So prime meaning that if a group is finitely generated and elementarily equivalent, then you can embed it inside of your group. I think this is right. And quasi-finitely axiomatizable, meaning that there is some finite collection, there's like some one sentence in the language of groups. Actually, wait. Maybe it is just this, that if it's maybe that there is some set of first order sentences such that if a group, if another finitely generated group satisfies them, then they're isomorphic. Maybe this is right. Yeah. Okay. I think I started more sure of my memory of this result than I ended up, unfortunately. Yeah. My sense is that no, it's not enormously difficult, other than the fact that it is in a language that I don't speak.
Sure.
but otherwise, it's not so bad. No.
Okay. Other questions?
Well, I am thinking of a question that probably doesn't make much sense, but in your context, well, definitely you interpreting certain kind of groups in one specified ring. What we are used to is to interpretations and bi-interpretations of one theory in another. So you have a class of structures. You have a first order class of structure. And then you have uniform bi-interpretation between all models on one side and with all models on the other side. So here, since you're talking about groups that are, finite generation, it's probably nothing that can be done in a first order way, but maybe in some language that's expressive enough. Then you have bi-interpretation between a class of structures on one side and this other class of structures on the other side. So instead of Z, perhaps you could have some more extended. Thinking about models of arithmetic, that how about interpreting structures in non-standard models as well?
So the thing is that right. My issue is that I don't know what sort of is the right extension of an arithmetic group, which is not finitely generated. Right? All arithmetic groups are automatically finitely generated. In fact, they're finitely presented more strongly.
Right, but in this case, you could go beyond first order by just saying, you know, in some L infinity,
right.
Saying, or you can express finite generation in an infinitary way, and then look at the sort of theories on the other side that are similar in nature.
Okay.
But it.
Yeah, I mean, fair enough. I guess I'm not. I don't have a good sense of what this would tell you.
No.
And I must confess that it's not something that I thought about much. Like at the end of the day, I'm a number theorist. I'm happy to use non-standard models in order to learn things about standard ones, but always my chief point of interest is understanding arithmetic. No, it's an interesting question, but not one I'm well equipped to answer, I guess.
Okay, other questions? Okay, let's thank Arseniy again.
Thank you, Sanya.
Thank you, Arseniy.
Thank you very much.
It was very good.
And
I'm glad.
MOPA is off next week, unless anyone would like to speak. So if you'd like to, let us know. But otherwise, we'll return in 2 weeks.